Facing forward. Tavion, you're supposed to be on IXL right now, unless you're checking Friday's assignment. Shamari, not here. Amari, not here. Other than that, everybody is here, I think.
Oh.
All right, I'm going to scroll.
It's hot.
We did those two together. Here's the back page. Anybody have questions on any of them? Jalen, did you do it? Caleb Bear, you do it? Denai, did you do it? Some of it? Did you check the ones you did? All right. Anybody have any questions on anything from Friday? Simplifying the radicals, but really they're just square roots, right? Okay, today we are going to be adding and subtracting square roots. It's rational expressions, but the rational expressions specifically that we're going to be working on are square roots, adding and subtracting square roots. Sorry? Yes, please. Go ahead and get off your Chromebook. I think you guys already have all that. All right, so your notes say 10-3, operations with radical expressions. We've actually multiplied and divided them already when we simplified them. So we are going to multiply and divide them, but today the new thing really is adding and subtracting them. So let's talk a little bit. Radicals are very similar to like terms, right? We can add and subtract only like terms. We can add and subtract only like radicals as well. But we can multiply and divide any radicals, any terms. So, for example, I want you guys to put example 1 in here. Ooh, that's good. So 2x times 3x squared. So 2x times 3x squared. Can anybody tell me what 2x times 3x squared is? 6x squared, right? Coefficient times coefficient, variable times variable, right? So that's x to the first if you don't see it there. So that's going to simplify to 6x cubed. I do. Which phone up here and I'll trade you for one. So we're kind of comparing like terms and operations with like radicals. We're supposed to be pretty good at this point with working with like terms and unlike terms. So operations with radicals, radicals do not have to be like to multiply or divide. So our first example is going to be 2 times the square root of 5 times 3 times the square root of 3. So remember, it's coefficient times coefficient. Now this was variable times variable, but this is going to be radical times radical, right? So what is 2 square roots of 5 times 3 square roots of 3? What's 2 square roots of 5 times 3 square roots of 3? Jacob, do you know? It's okay. 2 square roots of 5 times 3 square roots of 3. Coefficient times coefficient, right? Right, so remember, coefficient times coefficient, radical times radical. This is what we just finished working on for the last 3 or 4 days, 2 or 3 days. Okay? Another example, if we divide them, we can divide x to the 4th and x. Those are not like terms, so we learned how to divide those, right? Coefficient divided by coefficient. That's going to give us 4. X to the 4th divided by x to the 1st is going to be x cubed. That's right, x cubed. So this is stuff we've already learned, and we've also done it with radicals. 3 square roots of 15 divided by the square root of 5, those are not like radicals. So like radical means it's the same value under the square root symbol. Here, this simplifies, it's 3 divided by 1, because that's the coefficient here. There's not one that you can see, so that's a 1. The square root of 15 divided by the square root of 5 is the square root of, actually it's just, we can go straight there to the square root of 3. I don't know why. We're going to go straight to the square root, because we can divide that without doing anything else. We don't have to. So that's going to be 3, and the square root of 15 divided by the square root of 5 is the square root the square root of 3. Is that right? Actually, let me check something real quick. So we learned how to break it down into perfect square factors. So this would be 3 times the square root of 25 times the square root of 3 all over 5, and then that's going to simplify to 15 square roots of 3 over 5. And now that simplifies to 3 square root 3. The point is, maybe too long a time to make this point, but the point is, it doesn't matter that these are not the same. It doesn't matter that these are not like terms, right? However, when you're adding and subtracting them, they do have to be alike, whether it's like terms or radicals. Sorry, I'm doing what I put on here. Okay. So I think you already have this in your notes. So terms must be like to add or subtract. To combine, we add or subtract the coefficients. And so you already have that on your notes. So now we're going to look at this example. Example 3. 3x squared plus 5x to the 5th plus 2x squared. We can only add terms that are like terms, and that means same variable with the same exponent, right? So here, x squared and x squared, those can be combined because they have the same variable, the same exponent. This one is different. So to simplify this expression, we can only combine the things that have like terms. So that would be 5x squared plus 5x to the fifth power. We could not add them together because you can't add them together if they're not like terms, right? Mm-hmm. Exactly. So for this example, x 8z cubed minus 2z cubed, both of those are like terms, so we just subtract the coefficients. 8 minus 2 is 6. When you add or subtract them, that exponent on the variable is never going to change. So that would be 6z cubed. And it's the same way with like radicals. So like radicals means they have to have the same number under the radical. So like radicals have this like radicands. The number under the radical is radicands. If you don't like that word, you can write number under the radical. Like radicals have the same number under the square root. Is that too little? Can y'all read that? Oh, I'll type it. So like radicals have the same number under the square root symbol. So that's what I'm about to write in there. So for example, this would be example 3 over here. 5 square root of 5 plus 2 square root of 5. We're looking under the square root symbol. Those are the same numbers, so to add them, we just add their coefficients. So 5 plus 2 is 7. When you're adding and subtracting square roots, that number under the radical is never going to change. It can only change if you multiply or divide it. So here, 7 square root of 2 minus 8 square root of 2, that's going to be negative 1 square root of 2. But remember, just like a regular coefficient, we would just leave the negative out there. So it would be the opposite of the square root of 2. So it's also kind of like fractions. You can add and subtract fractions with like denominators only, but you can multiply or divide fractions no matter if they're like denominators or not. So it's the same idea for square roots. Aiden? Yep, 7 minus 8 is negative 1 times the square root of 2. Or we just say negative square root of 2 or the opposite of square root of 2. Okay, so if radicals aren't simplified, we simplify them to see if they can be combined. So I think you can do this underneath what we just finished before we go to the second page. So if radicals aren't simplified, we simplify to see if they can be combined. So let's put this example in, and I think this would mean, I don't know, example 5 we can say. Doesn't really matter. You just write example. 4 square root of 7 plus 2 square root of 28. It looks like right now that they can't be added because the number under the radical isn't the same, right, Paul? But we have to check first to see, is that number simplified? If that radical or square root is not simplified, we simplify it first and then see if we can add or subtract them. The 2 square root of 28, is there a square root factor of 28? Caleb says yes. What is it, Caleb? 14, and 4 and 7. Yeah, 4 and 7. So we can rewrite that. So 2 squared root of 28 is not simplified. So now we're going to rewrite that. 4 squared root of 7 plus 2 times the square root of 28. We broke that down to its perfect square factor here, right? So now what is the square root of 4? Right, the square root of 4 is 2, so let's stretch that out there. So now what is 2 times 2? Yes, so now 2 times 2 is 4. So now we have 4 square root of 7 plus 4 square root of 7. Does that make sense? So now we add the coefficients because now we have the same number under the radical. So adding the coefficients simplifies that expression to 8 square root of 7. At first glance, example 5 looks like we cannot subtract these, but we can't say for sure until we simplify the square root in each term. So neither of these radicals is simplified, and I know because off the top of my head I know 16 times 2 is 32, and that's a perfect square factor, right? 9 times 2 is 18, and that's a perfect square factor. If you don't recognize a perfect square factor automatically, you make a list like we did here, right? So now we're going to rewrite this term as 5 times the square root of 16 times the square root of 2. And we're going to rewrite this term as 4 times the square root of 9 times the square root of 2. And then we simplify our perfect square factor. So square root of 16 is 4, the square root of 9 is 3. 5 times 4 is 20, square root of 2, minus 12, square root of 2. Just for the record, even if you can't add or subtract them, this is part of simplifying it. If they say 5 square root of 32 minus 4 square root of 18, you have to give it in simplest form. So if these are different, it would still be mandatory that you do that. Does that make sense? So 20 minus 12 is 8 square root 2. Remember, anytime you're adding or subtracting a square root, the number under the radical doesn't change. The only way that can change is if you're multiplying or dividing it. Any questions? Okay, so that's the pretty straightforward part. It's going to get a little bit more complicated. Remember when we have a radical in the denominator? We had to multiply and get that radical out of the denominator for the first part of this chapter. Y'all remember that? Oh, this is actually a pretty easy part right here. So let's go ahead and put in this example. So we're going to multiply radicals using the distributive property. You do not have to title it. I just want you to see this example. So this is 3 times 2x. Actually, let's not even do that. We're going to go down to this one. This is 3 times 2 square root of 5 plus 3. All right? It's not example 3. It's 3 times 2 square root of 5 plus 3. Does that make sense? Distributive property tells me to do what? Multiply what's on the outside by everything on the inside, right? So if we're multiplying 3 times 2 is 6 square root of 5, 3 times 3 is 9. Those aren't like terms, they're not like radicals, because they're not a radical in this one, so that's simplified. That's the simplified expression. Now what if the number or the value on the outside is a square root? So let's look at this example. The square root of 2 times the square root of 6 plus 5. Same thing, it gets distributed. What is the square root of 2 times the square root of 6? What is the square root of 2 times the square root of 6? Square root of 12. And the square root of 2 times the square root of 5? I'm sorry. Square root of 2 times 5, not the square root of 5. So that's the difference here. There's no square root here. It's just 5 square root 2, right? I confused you guys. So the square root of 12 plus 5, is that my final answer, do you think? What do you think? Is that my final answer? Is this radical simplified? Is that square root, is there a perfect square that I can factor this into? So 1 times 12, 2 times 6, I want to do my 4 first, so 4 times 3, because 4 is a perfect square, right? So now, we've distributed, but once we distribute, if we can simplify the square root, then we have to go back and do that. So now the square root of 12 is the square root of 4 times the square root of 3 plus 5. Square root of 4 is 2, right? So that's 2 times the square root of 3 plus 5. That would be your simplified expression. What does it mean if you have the square root of 11 minus 2 all squared? What does that mean? Raised to the second power. Do you know what that means? What's it mean if we have 3 squared? Three times 3, right? 3 squared is 3 times 3. So the square root of 11 minus 2 all squared. So we've got to rewrite that as the square root of 11 minus 2 times the square root of 11 minus 2. And then we use double distribution or FOIL, depending on who you had for algebra. So the square root of 11 times the square root of 11 is 11. Remember, anytime you multiply a square root by itself, it's the number under the radical. And then the square root of 11 minus times negative 2 is negative 2 square roots of 11. You with me? So we've multiplied this first term by everything here. Now we've got to multiply this term by everything here. So negative 2 times the square root of 11 is negative 2. Yes. And negative 2 times negative 2? Positive 4. So now we go back and we combine like terms. So 11 plus 4 is 15. And negative 2 square root of 11 minus 2 square root of 11 is minus 4 square root of 11. So that is the simplified expression. If there was something underneath here we could simplify, we would simplify at that point, right? That 11 is prime. What do you think? So far, so good? Sydney, are you writing what we're writing? Are you writing what we're writing, Alani? Okay. All right, so now we're coming to one other thing. Ooh. Well, let's go and do this one. Before we do our conjugates, let's do this one. So one more example. Square root of 6 minus 2 square roots of 3 times 4 square root of 3 plus 3 square root of 6. So double distribution again, or FOIL, first, outside, inside, last, depending on who taught you algebra. So the first terms get multiplied. So that's going to be 4 times the square root of 6 times the square root of 3. 4 square root of 18. Does that make sense to everyone?
Yeah.
All right, now we've got the square root of 6 times 3 square roots of 6. What's the square root of 6 times the square root of 6? 6, right? Square root of 6 times the square root of 6 is 6. But we've got this times 3, right? So what we have is, we have 3 times 6, right? So this is plus 3 times 6, because the square root of 6 times the square root of 6 is 6, and it's times 3. Now we have this second term, got to get multiplied by both in here. So negative 2 square root of 3 times 4 square root of 3. What's negative 2 times 4? Negative 8. And now square root of 3 times square root of 3 is 3. And negative 2 square root of 3 times 3 square root of 6. Coefficient times coefficient, square root times square root, right? Ah, there you go. Negative 6 square root of 18. So we're going to simplify. These are like radicans. We can go ahead and simplify those. So 4 square root of 18 minus 6 square root of 18 is negative 2 square root of 18. And now this is plus 18 minus 24. Is everybody following me? So these can be simplified, and this radical, the square root, can be simplified, right? What's the perfect square factor of 18 that we can break this down into? 2 and 9, that's right. We're going to put our perfect square factor first. So negative 2 times the square root of 9 times the square root of 2, and 18 minus 24, that's minus 6. Tavion, are you writing what I'm writing? Tavion, turn your shoulders to face the front. All right, what's the square root of 9? So this is negative 2 times 3, so that's negative 6 square root 2 minus 6. And that would be your final answer. You all caught up with me? All right, you don't have to write anything, just look at this one, but I almost messed up at the beginning. So here, this example, we had 3 square root of 15 divided by a square root of 5. In order to get that radical out of the denominator, we had to multiply top and bottom by square root of 5, because the square root of 5 times the square root of 5 is 5, and now we don't have a square root in the denominator. Does that make sense to everyone? Sometimes you're going to have 2 terms in the denominator, though. So if one or both of them are radicals, you've got to have a different strategy to get that out of the radical. So I'm going to show you one before we get there. Let's see. So let's say, one example before we get to our conjugates. Let's just say 3 over the square root of 5 minus 2 square root, no, actually, no, let's make it even simpler, minus the square root of 3. All right, so we have radicals in the denominator. In fact, of 2 terms, right? So the only way to get rid of this is to use that difference of squares concept. So if we multiply exactly the same thing, but a different operation, then we're going to get rid of the radicals. So here, we're going to multiply this by the square root of 5, not minus, but plus the square root of 3. Why do you think we're going to do that? I'm going to show you. What's the square root of 5 times the square root of 5? Nope. What's the square root of 5 times the square root of 5? 5, right? Square root of 25, so that's 5. And that's square root of 15, so plus the square root of 15. Let's do a different color here. Square root of 3 minus 5, or times the square root of 5 is minus the square root of 15. And the square root of 3 times the square root of 3 is what? 3. So that's minus 3. So what is the square root of 15 minus the square root of 15? 0, right? So when we multiply by the exact same binomial, but with a different operation, what's going to happen is it's going to be the square of the first term minus the square of the second term. So it's always just going to be 5 minus 3, like this here, right? So this 5 minus 3 is going to simplify to 2. But whatever we do to the denominator, we have to do to the numerator. So here we're going to multiply this by the square root of 5 plus the square root of 3 and put it in parentheses. You follow me, Jacob? You follow me, Caleb? Jalen? So now this is 3 times the square root of 5, which is 3 square root 5, plus 3 times the square root of 3, which is 3 square root 3. Can't simplify that. They don't have the same numbers under the square root. And this is 2. So it's 5 minus 3. So it's 2. So that would be our final answer. So anytime we multiply a binomial by its the factor that gives us the difference of squares, all we have to do is square the first term minus square the second term, minus the square of the second term. So here, if a denominator is a sum or difference of radicals, the denominator must be, this is what you're filling in, rationalized. So this red is what you're writing in your blank. A sum or difference, that means if we're adding 2 terms or we're subtracting 2 terms with a square root in it, we can rationalize it by using the method of a difference of squares. And in order to do that, we multiply the denominator by its conjugate. Well, what the heck is its conjugate? Let's write that first. Multiply the denominator by its conjugate. Conjugate is the exact same expression, except you do the opposite operation. And I cannot remember how I wrote that here. So. Same 2 terms of the original with the opposite operation. So the terms are the same except if it's addition, you switch it to subtraction. If it's subtraction, you switch it to addition. So for example, if this were our denominator, the conjugate, oh wait, I know, it's a lot.
Mm-hmm. You will. It's giving me a headache.
Just think, I'm having to write it and say it, Aiden. I have a headache and a sore throat.
I don't feel good.
Oh, I'm not sick, I just have talked too much. I've been talking all day. Alright, so the conjugate would be the square root of 11, square root of 5, and instead of subtraction, it would be addition. So you're writing this example. The conjugate is exactly the same terms except you switch this to a plus. And the reason we do that is because if you multiply them, we're still in the middle of notes, buddy. Alright, so the reason why we do this is so we'll get rid of the square root. So anytime you multiply a radical expression by its conjugate, you're going to get rid of those square roots. Now, we just talked about this. We're not going to do it the long way this time. Now, this time we're going to use the shortcut. So, square root of 11 minus 5 times the square root of 11 plus 5. We're going to use the shortcut here. It's going to be the square root of 11 times the square root of 11, which is 11, minus 5. So when we multiply those conjugates, we get 6. Okay, and that we want to do that because we're worried about getting the radicals, the square roots, out of our denominators. So your steps are, here are your steps. You don't have to write any of that. We're going to write your steps, and then we're going to do this example together. Right, the steps are multiply the denominator. So I've given you everything. You're going to put your filling in the blank with the denominator. Multiply the denominator by its conjugate, actually. The denominator by is what you're writing here. Then you're going to multiply the numerator by the same factor. Then you're going to simplify all radicals, combine like terms, so that's what you're filling in this one. Then simplify again if necessary. So the part you're filling in is a dotted line. Once you're through with that, go ahead and write this example down. Can you tell me what the conjugate is going to be? What is the conjugate of the square root of 10 plus the square root of 5? Papa? Perfect. So the conjugate is the square root of 10 minus the square root of 5. So what we're going to do is we're going to multiply the original expression, negative 3 divided by the square root of 10 plus the square root of 5, by the conjugate in the numerator and denominator. So we're going to put this in parentheses because this has to be distributed. This, however, we're going to use the shortcut. So I'm going to wait and let you guys get caught up with me. So the original expression times the conjugate in the numerator and the denominator. So the conjugate of the denominator has to get multiplied by the numerator and the denominator. Basically, we're multiplying it by a different form of 1, right? You can multiply any number by 1 and it doesn't change its value. So the numerator here would be negative 3 times the square root of 10, or negative 3 square root 10. And then negative 3 times negative square root 5, so plus 3 square root 5, all over, when we multiply these, we're going to take the shortcut now. We're not going to do the long method. It's always going to be square root of 10 times the square root of 10 is 10. It's always going to be minus. Square root of 5 times the square root of 5 is 5. That's always what we're going to do. So now this simplifies to negative 3 square root 10 plus 3 square root 5 divided by 5. The 5 can't simplify because this is the square root of 10, the square root of 5. If these were both 5, we could simplify something, but that is our final answer. What do you think? What do you think, Jacob? Let's do this one. Negative 2 divided by square root of 6 plus square root of 11. Can't have those radicals in the denominator. The only way to get rid of that sum of radicals, or any radical that's being added to some other unlike term, is to multiply the numerator and the denominator by its conjugate. What do you think the conjugate is here? It is going to be, yes, but what is the conjugate? See, that's the product of the conjugate you just gave me, right? So you're right, that's what's going to be in our denominator, but I need to know what to multiply the top by as well, right? So what is the conjugate of the square root of 6 plus the square root of 11, Jalen? Perfect. So if I multiply the denominator by that, I've got to multiply the numerator by that. So now, yeah, we've already done that. So we're going to do that again. All right, so this would be negative 2 times the square root of 6 minus the square root of 11 all over 6 minus 11. So remember, square root of 6 times the square root of 6 is 6. Always going to be minus square root of 11 times the square root. It's always going to be the first one squared minus the second one squared. It's never going to be plus. Always going to be the first one squared minus the second one squared. So the numerator is going to simplify to negative 2 square roots of 6 plus 2 square roots of 11. The bottom one's going to be negative 5. Usually they don't want you to keep the negative in there, in the denominator. So if we rewrite this with a positive denominator, we just switch all the signs. So that would be equal to 2 square root of 6 minus 2 square root of 11 all over positive 5.
Yeah.
Oh, we're not doing golden rectangles. All right. Anybody need me to go back any place?
No.
Where at, Caleb? Okay. Here? All right, you guys are doing the even problems for homework, right? Not the odd ones. We'll do the odd ones tomorrow.